qubit code, which is just the repetition code concatenated on top of the dual repetition code, or vice versa, the dual repetition code, the repetition code in the X basis concatenated on top of the standard repetition code in the Z basis. So I'd like to start today just by talking about more codes. And all the codes I'll talk about are stabilizer codes. So the stabilizer code is it's a stabilizer state where we don't have as many independent stabilizers as qubits. So if you have n qubits and you have m stabilizers, so these are independent commuting Pauli operators on n qubits, and the number of degrees of freedom, the number of encoded qubits is n minus n. So for example, so this is a simple example. Here's a 3-qubit code, you could say, where the stabilizers are IZZ and IXX. So of course, XX and ZZ stabilize the cat state. And so on 3 qubits, what this is saying is that actually the first qubit is free. It could be anything. And the second two, the qubits 2 and 3 are in a cat state. So this is, in a sense, it's a code. If you want to do the encoded X operation is just X on the first qubit. The encoded Z operation is Z on the first qubit. It's not a very interesting code because, like, there's no error protection, for example. Formally, you could say this is a code. There are more interesting codes. So here are just a few examples of slightly more interesting codes. So the 913 code. So what these parameters mean is, all right, so first of all, if you have a single bracket, like for example, like this means single bracket means a classical error correcting code. Double brackets means quantum. Just what we do. All right, so double brackets, and then the first parameter is the number of physical qubits. The second parameter is the number of encoded qubits, and so the difference is the number of stabilizers. So this is 8 stabilizers. And the distance, so the distance it's the least weight of a non-trivial logical operator. So for example, I'll do some examples. Here, this is an interesting code. This is a 513 code. I don't think it has like a special name. I think you just call it the 513 code. And so here there's 5 physical qubits, 4 independent stabilizers. Here are the stabilizers. So X, Z, Z, X, I, and its cyclic permutations. So cyclic rotation. So X, Z, Z, X, I, X, Z, Z, X, I, and X, Z, Z, X, I. And that's only 4 of them. There's another cyclic permutation, which is X, Z, Z, X, I. But that 5th one is it's dependent on the first 4. It's actually, I think, the product of the first 4. Is it? Right, so if you multiply these together, you get Z plus or minus Z, Z, X, I, X. Yeah, which is what we wanted. Right, so there's only 4 independent ones, so you do have one encoded qubit. And you can see what the encoded qubit is. Logical X, you could choose it to be, for example, X to the 5, X tensor 5, and logical Z would be Z tensor 5. This does commute with, this commutes with all these, this commutes with all these, and these two anti-commute with each other. So they're valid, logical X and logical Z. And so this looks like it's a distance 5 code. These operators have weight 5, but actually it's not distance 5, it's still only distance 3 because there's lower weight operators that are equivalent to these. So for example, so for example, if you take this operator and you multiply by the first stabilizer, that gives you I, Y, Y, I, X. So I, Y, Y, I, X. That's a weight 3, Y, Y, I, X. That's a weight 3 operator that does logical X, and so that's the least weight operator that does logical X, Y, or Z. So this code is distance 3, because any operator equivalent to X, Z, or Y has to have minimum equivalent weight at least 3. And this is the smallest code on qubits with distance at least 3. You can see that because this code is what's called perfect. So perfect means